Oftentimes we forget to think about how prevalent differential equations can be in our daily lives. We drive a car to work, accelerate it, and decelerate it, changing our velocity over time and our position over time. We throw a ball up in the air and watch its parabolic arc across the sky, watching it land in a relatively predictable spot. Even more predictable if we consider wind and air resistance. Sometimes we even like to ask ourselves rather asinine questions such as, what if everyone on Earth stood in the same city and jumped and landed at exactly the same time, just for the sake of seeing what would happen? All of these are kinematics problems, and furthermore, all of these can be modeled using differential equations.
Almost all kinematics use some sort of change in position and velocity over time. Even changing acceleration over time in cases of springs. Remember that change in value over change in another value is a differential. And remember from Physics 101 that velocity is the derivative of position and acceleration is the derivative of velocity. And the second derivative of position equation, such as projectile motion, once expressed as a parabolic function of velocity, acceleration, and the initial position as constants with respect to time, can be expressed as first or second order differential equation with the respect to a given position function.
We're going to explore two specific cases in kinematics that use differential equations in the modeling. One, a rather asinine, funny, and silly application as a first order differential equation, and the other, a more everyday application as a second order DE. The first example will be an astronaut with indigestion aboard the International Space Station. The astronaut propels themselves forward upon a large fart and is slowed down by a drag force, but otherwise unaffected by a force due to gravity. The other is a model of the angle made by the swinging of a pendulum that is undampened, such as the effectively undampened swinging of a grandfather clock's pendulum.
For the first order differential equation, we are going to specifically explore the power series expansion of the differential equation and compare it to the exact value we get from an exact solution we define to be the actual velocity generated by the astronaut's fart. We are then also going to use Euler's method to estimate the solution for a given time and compare it to the power series in exact solutions numerically. Likewise, for the pendulum, we are going to similarly generate a power series solution and compare it to the exact value graphically to determine the error produced by the power series solution. So, without further ado, let's get right into it.
Imagine you are an astronaut aboard the International Space Station. You get a bad case of ingestion, make sure nobody's around, and let one rip. This ends up propelling you forwards slightly with a given velocity function, and you slow to a stop as the air resistance slows you down. This scenario was specifically chosen to get rid of gravity in a fluid drag situation, while also creating a humorous situation to visualize. Let us assume that this fart propel you with a velocity function that we are absolutely sure of. Something simple like v of t equals e to the negative t. This function was specifically chosen as it is slightly believable for this situation in the equation in question, and the fact that the ordinary point t of 0 is simply 1.
We know that the drag force function, when gravity is removed, can be expressed as the dE v prime plus bv equals 0, where b is some proportionality constant that's defined by your cross-sectional area, mass, and the fluid dynamics. And for calculation's sake, we'll just say that b equals 1. Thus, the dE simply becomes v prime plus v equals 0. So now we want to convert this to a power series. And we know that for any given function, the power series expansion of the function can be expressed as v equals the sum from n equals 0 to infinity of a sub n times t to the n, where a sub n is some currently unknown constant. We know that the derivative of this v prime equals the sum from n equals 1 to infinity of a sub n times t to the n minus 1, where the index can start at either 1 or 0, due to the 0th term being 0 anyway.
We then substitute these two values into the original differential equation and normalize the indices and power attached to the t so that they match and are compatible. Remember that if you drop an index by 1, all the other values must go up by 1 and vice versa. This is where it's handy to start the power series at 1. We then see that we can combine the power series together. Since this is an ODE and everything equals 0, it automatically means that all coefficients must equal 0. Thus, we can extract the coefficients and set them equal to 0. We have a sub n plus 1 times n plus 1 plus a sub n equals 0. It obviously follows through simple algebra that trying to isolate the largest subscript gives us a sub n plus 1 equals negative a sub n divided by n plus 1.
We know a sub 0 is free and defined by our ordinary point. We then write out the first few terms of this sequence to see what the pattern is. For n equals 0, a sub 1 equals negative a sub 0 over 1 factorial. For n equals 1, a sub 2 equals positive a sub 0 over 2 factorial. You can look at the table here to see the first 8 terms of the expansion. But wait, we see a pattern here. This a sub n equals negative 1 to the n times a sub 0 over n factorial. We know from our ordinary point that at t equals 0, we get 1. Thus, a sub 0 equals 1. This then, in the series form, is v equals the sum from n equals 0 to infinity of negative 1 to the n times t to the n over n factorial. Here is the exciting part. This power series expansion is equal to exactly our original function, e to the negative t. So this approximation is less so an approximation and really is an exact solution, at least for the ordinary part chosen and the value of b chosen, that is.
But what of another method? What of Euler's method? We can estimate the solution to this DE using Euler's method. There's other methods like Runge-Kutta method, but for now we're just going to focus on the simpler, less accurate Euler's method. It is simple, just like me. So take your ordinary point. Define a step size that steps away from that ordinary point at regular intervals. Add your step size times the derivative of your given function evaluated at that point. Now mark a coordinate point at that stepped away ordinary point and this new point. Make this the new point and recursively step through this method over and over again.
We are going to use some C code, written by me, that computes these values for us. This code is available as a copy and pastable text in the written document, but is provided on the screen for current reference. The code essentially steps through Euler's method with progressively smaller step sizes and calculates the error from the original function, which is the same as the power series solution, and calculates the percent error from the original. It is possible to set values for the starting value, step size, and a faraway point.
As you can see from the results of setting the step to 0.1, the error grows very rapidly and ends up being over 100,000% error. By the time it reaches t equals 10, now if we can decrease the step size drastically, we can see the error at 10 drop considerably. If we decrease it even more, the error is only about twice the true value of the equation. Note the computational time at the bottom of the command window for all of these. They increased dramatically as step size increased. While this method is quick and can be done by hand for certain DEs, it is not necessarily the most efficient nor the quickest method, like the bubble sort of sorting algorithms, but for a differential equation estimation. So while you as an astronaut may have experienced some bad indigestion, at least you can be rest assured that physics and differential equation will be there to catch you.
Now we explore the slightly more convoluted example of a second order DE, the angle that an undampened pendulum makes over time for small angles. Using the small angle approximation where sine of theta is approximately theta for small values of theta due to the small deviation of angles smaller than 12 degrees. So let's say we're observing a grandfather clock whose dampening will be negligible over any reasonable observation time frame due to the fact that, well, the pendulum needs to be regular for the clock to function normally. So the ordinary DE that models the behavior angle of the pendulum can be expressed as theta double prime plus g over L times theta equals zero, where L is the length of the pendulum and g is the acceleration due to gravity. We know from basic physics that the exact solution is theta equals theta max times the sine of the square root of g over L times t. We explained how to solve power series earlier, so we will simply show the work on the screen to avoid reiterating ourselves. The only important thing of note is that now we have theta double prime, which is equal to the sum from n equals 2 to infinity of a sub n times n minus 1 times t to the n minus 2, which is then plugged into theta double prime.
Our recursive function, then, as can be followed, is a sub n plus 2 equals g over L a sub n over n plus 2 times n plus 1. We then do the similar process as before with the table, separating the values for a sub 0 and a sub 1 into even and odd values of n, and creating two power series that are defined by the equations on the screen. Thus, theta is approximately a sub 0 times the first power series plus a sub 1 times the second power series. But wait, we know these power series. They're the series expansions of sine and cosine, with the constant coefficient within it.
Thus, our series approximation formula becomes theta equals a sub 0 times the cosine of g over L times theta plus a sub 1 sine of g over L times theta. Evaluating our ordinary point exact solution at the theta and theta prime, we get the coefficient of 0 for a sub 0 and square root g times pi over 24 for a sub 1. Thus, our approximation at pi over 24 radians becomes square root g times pi over 24 times the sine of g times t.
We can see that the approximation is very poor at pi over 24 radians, as it is pushing the limits of the small angle approximation as well as the limits of the DE. But what we can tell is that for the ordinary point, there is no error. The exact solution here is depicted in blue, and the approximation is depicted in red. However, it is important to note that due to the nature of sine and cosine, the error will not be too great at any point in the curve, but this is not a reliable method to estimate the angle of the pendulum.
In conclusion, we have seen many applications of differential equations throughout this course. We have seen how to solve them, handle them, pick them apart, construct them, analyze them, and so much more. At this point in a math course, one is in a differential equations class, most likely because of an engineering degree, and almost certainly kinematics will either come up or be a fundamental part of one's career as an engineer, regardless of what field of engineering one goes into.
We have seen that differential equations can have numerous applications from very serious topics such as time-keeping mechanisms to absolutely inane and absurd topics such as gassy astronauts. Regardless of what we are solving, we need to know how to solve them because what we can apply for something silly can be memorable topic to help you learn from a more complex and more serious topic later on. Understanding the power series is fundamental to both applied and pure math. And as power series approximation are how calculators actually evaluate square root, pi, e to the x, logarithm, and all sorts of functions that once mathematics and engineers had volumes of reference books of tables to go by.
Kinematics as a whole are inseparable from differential equations. Pun intended. Understanding differential equations and how to solve them is an essential part of understanding kinematics, and as such, an essential part of an engineer's career. Without differential equations, kinematics would be much harder to predict and understand due to chaotic motions, so it's important to know how to solve them. We hope that you enjoyed our little presentation about kinematics, power series, and differential equations. We hope that you enjoyed our little presentation about kinematics, power series, and differential equations. And hope that next time you drive a car, look up at a pendulum, or look up to the ISS and wonder about the gastrointestinal distress of its passengers, you'll at least remember how prevalent differential equations are throughout our daily life.